In this video, we're going to scroll through the data from subject number 1 in the ERP Core Mismatch Negativity Experiment, which has the kinds of artifacts we see in most studies with adults. I'm going to go pretty quickly, and I encourage you to follow along in EEG Lab, pausing the video when you want to take a closer look. You can find the data for subject number 1 in the MMN Data folder. After loading the data set into EEG Lab, I launched the scrolling plot routine. I'm going to set the vertical scale to 200. The EEG channels are at the top, and then we get to the EOG channels. We have separate channels for horizontal EOG left and horizontal EOG right. We also have a channel for vertical EOG lower, which was under the right eye. These channels are all referenced to the average of P9 and P10, just like the EEG channels. At the very bottom, we have bipolar EOG channels. The HEOG bipolar channel was created by a subtraction of HEOG left minus HEOG right. The VEOG bipolar channel was created by a subtraction of VEOG lower minus FP2. We always begin the recording 10 to 20 seconds before stimulus presentation begins. So this is the EEG while the participant is just sitting there waiting for something to happen. We usually see lots of artifacts before and after trial blocks, and this is no exception. Here we see what looks like a burst of EMG activity, high-frequency spikes that happen when a muscle contracts. It's largest over lateral, frontal, and central channels, so my guess is that it's coming from the temporalis muscle on the right side, which is close to these electrode sites. The temporalis muscles are used for closing the jaw. They're big muscles that often produce large artifacts in EEG recordings. Here we can see a horizontal eye movement. The HEOG left channel goes slightly negative, and the HEOG right channel goes positive at the same time. The bipolar channel is HEOG left minus HEOG right. A negative minus a positive is an even bigger negative, so we get a big negative deflection in the bipolar channel. It's arbitrary whether you do left minus right or right minus left, as long as you know which direction you did the subtraction. Do the eyes move leftward or rightward here? The key to figuring this out is to remember that each eye has a dipole that's positive in the front and negative in the back. When the eyes rotate, the dipole rotates. Pause the video and try to figure out which way the eyes moved here. Okay, here's the answer. This was a rightward eye movement. When the eyes moved rightward, the positive side of the dipole points rightward and the negative side points leftward. This gives us a negative voltage in HEOG left, a positive voltage in HEOG right, and a large negative voltage in HEOG left minus HEOG right. Let's scroll 5 seconds, which is just one click. Things have generally gotten a little flatter, except that there are still lots of horizontal eye movements. You can also see some tonic EMG activity in these frontal channels. That's probably coming from the corrugator muscles of the forehead. If you see a lot of this while you're doing a recording, you can ask the participant to relax their forehead, and it will usually go away. Here we see an eye blink. It has the classic shape of an eye blink, kind of like a mountain that's skewed to the right. It's positive above the eyes. The voltage is largest in the FP1 and FP2 channels, and then fades as we move posteriorly. Another important property of blinks is that they invert in polarity under the eyes. If you look closely at the VEOG lower channel, you can see a negative going voltage at the same time as the positive going voltage at FP1 and FP2. The VEOG bipolar is VEOG lower minus FP2, so we have a negative minus a positive, which gives us a large negative deflection. Unfortunately, it's a little cut off on the screen. Here's a little trick that makes it easier to see blinks. If you click the stack button, it puts all the waveforms on top of each other. Blinks really stand out because of the polarity reversal under versus over the eyes. Let's change the scale to 50 to see the blink better. Now you can get a better sense of its shape. Okay, let's click spread to go back to normal and set the vertical gain back to 200. What's this over here in the OZ channel? I have no idea. It's just at one site, so it's very unlikely to be brain activity, which spreads as it passes through the skull and scalp. If we scroll another 5 seconds, we see more random up and down deflections in OZ. If we scroll another 5 seconds, we see that the task has begun because these vertical lines represent event codes. The OZ channel flattens out once the stimuli start, so I'm not too worried about it. If it kept going up and down after the stimuli started, I'd be worried that it was a bad connection, and I might interpolate it. Now that the stimuli have started and the waveforms are cleaner, I'm going to set the vertical gain to 50 so we can see the details of what's going on. We can see another little burst of muscle noise between 17 and 18 seconds, again at the right frontal and central sites. For most ERP analyses, this kind of occasional high-frequency noise isn't much of a problem. It gets filtered out. If we scroll another 5 seconds, we can see some alpha, starting around 23 seconds. If you counted the peaks, you'd see about 10 peaks per second, which is how I know it's alpha. Ordinarily, it would be more posterior, larger at the occipital channels than at the frontal channels. But every brain is different, and this participant's alpha is more centroparietal. If we keep scrolling, all we see is beautiful EEG. There isn't much drift, and I'm not seeing any blinks or eye movements. If only all subjects were like this. But let's not get too excited. Things sometimes go downhill as the recording progresses. If we look here around 92 seconds, we can again see some alpha. But something sticks out to me. The P7 channel is much flatter than the surrounding channels. At first, I was concerned that something might be wrong, but then I remembered that these data are referenced to the average of P9 and P10. P7 is so close to the reference that it's getting nearly identical activity, so not much is left after we reference the data. This is just another example of why you always need to think about the reference electrode and avoid the temptation of thinking that the signal in a channel named P7 is solely showing you activity from the electrode of the same name. If we scroll a little further, we can see an eye blink just before 98 seconds. And here's a big muscle burst a couple seconds later. But this is still beautiful EEG. If we keep scrolling, we can see something going on in the C5 channel around 125 seconds. It just starts going crazy. Calms down a bit starting around 141 seconds, but then it goes crazy again around 150 seconds. To be honest, I have no idea what might cause this pattern. It's just a rare idiosyncratic artifact. But it's not brain activity because it's limited to a single electrode site. I'm thinking this electrode might have a bad connection, and we may need to replace this channel with interpolated values. I'll explain how that works in the text. Now let's look at this segment between 175 and 180 seconds. We see a lot of alpha, but that's normal. It probably means the subject is getting a little drowsy. If I were doing the data collection, I might offer the participant a caffeinated beverage during the next break. And here's a blink at 179 seconds. Occasional blinks are perfectly normal. We can also see more drifting in the C5 channel. I'm definitely concerned about that channel. And now we see something new, high-frequency activity in the F8 channel. High-frequency activity like this is almost always EMG. Because the muscles are outside the skull, right under the skin, you can sometimes get EMG activity at a single electrode site like this. If we keep scrolling forward, we see that this high-frequency noise isn't going away. In fact, once we get to around 295 seconds, it starts getting worse. And now around 330 seconds, it's just huge. Here's a big EMG burst right after 339 seconds. You see it in all sites, so it might be being picked up by the reference electrodes. P9 and P10 are close to the neck muscles, so if you see noise in all sites, it might be from the neck. The mastoids are even closer to the neck muscles, making the noise worse, which is one reason we're shifting to P9 and P10 as our standard reference. But notice that this noise is a lot bigger in some channels than in others, so it's probably not coming from the reference. Noise from the reference should be approximately equal at all scalp sites, because the reference is subtracted from all these sites. My guess is that the participant is just stretching at this point, contracting lots of different muscles. This isn't a problem. It's easy to detect and throw out occasional segments of EEG like this. If we keep scrolling, we can see that the waveforms are getting progressively noisier. If we compare this segment at 365 seconds to this segment at 200 seconds, you can see that there's just more noise all over. That's how things go sometimes. Participants start getting uncomfortable or bored and the signal just gets worse. So you really need to look at the EEG from the whole session. Now, it'd take a long time to go through the whole session looking at 5 seconds at a time. So I recommend looking at parts of the session on that time scale and then looking at 60-second segments to see the whole session. You do that by going to the plotting window and selecting Settings, Time Range to Display. If we go back to the start, we can see the noisy part before the stimuli start, and then it gets super clean. Here's the EMG burst we saw before around 100 seconds, and you can see the eye blinks right before and after. Again, we can click Stack and change the scale to see the blinks better. When we scroll to the next screen, we can see that C5 is starting to act up, and toward the end of the screen we can start to see the high-frequency noise in F8. If we keep scrolling, we can see that blinks are starting to occur more frequently, and everything is starting to get noisier. You'll want to go back and forth between the 60-second view and the 5-second view when you're looking at data. I also recommend taking detailed notes during the recording that indicate periods of time with potentially problematic signals. Then you can go right to those time points when you look at the data offline. I hope you can see the value of looking through the whole session offline. If you just run your data through a script that treats every participant the same, some really crappy data will get through and contaminate your average ERPs. Every participant is different, so you need to tailor your artifact detection for each individual's data.